Okay, so now we're up to Chapter 7, Ethernet switching. And so basically, we're still talking about the data link layer, but we're talking about how Ethernet implements its data link layer through switches. So we're going to explain how Ethernet works in a switch network, and we'll look at the frame format for an Ethernet frame. We'll look at how Ethernet MAC addresses work, how a switch builds its MAC address table, which is what it uses for forwarding frames towards hosts. And we look at switch speeds and forwarding modes as well. Okay, so Ethernet frame. So again, we're talking about Ethernet, so it's the bottom two layers. We mostly think about layer 2, but of course, it still is involved in layer 1 because, you know, it does send the data over an Ethernet cable. And so, of course, Ethernet, we're talking about 802.3 standards. Now, 802.2 is actually that logical link control, that LLC. All right. So, the 802 standards, the logical link control sublayer, 802.2, places information in the frame to identify which network layer protocol is used for the frame. And then the MAC sublayer is responsible for the data encapsulation and media access control and provides data link layer addressing. And that's why we call it a MAC address. All right, so the MAC sublayer is responsible for data encapsulation and accessing the media. And so the encapsulation, of course, includes the frame format. So how do we organize an Ethernet frame? The addressing as well, so source and destination MAC addresses, and error detection as well. So the frame check sequence, which is stored in the trailer, as we said. So the MAC sublayer includes specifications for different Ethernet communication standards over various types of media, including copper and fiber. So as you can see, there's 802.3U is fast Ethernet, 802.3Z is gigabit over fiber, 802.3AB is gigabit over copper, 802.3AE is 10 gig over fiber, and so on. So there's a whole pile of different 802.3 standards for all those different ones. So legacy Ethernet using a bus topology or hub is a shared half-duplex medium. Ethernet over half-duplex medium uses a contention-based method, or CSMA-CD, which we spoke about last chapter. Ethernet LANs of today use switches that operate in full duplex. And so full duplex communications with Ethernet switches do not require access control through CSMA-CD. So thankfully, it's irrelevant now. All right, so the Ethernet frame. So the minimum Ethernet frame size is 64 bytes, and the maximum is 1518. So the reason we have a minimum frame size for Ethernet is for back in the dark ages, when we had CSMA-CD working, it actually had, the frame had to be big enough so that it could actually sort of fill the network, and you could actually detect that collision. And so that's why we had a minimum frame size. The preamble field is not included when describing the size of the frame. So the preamble, I think I might have mentioned it when we were talking about the physical layer. Remember, it was a 1 followed by 0 followed by 1 followed by 0 for 8 bytes worth of. Just again, that was the older standard so that you could synchronize the clock of the sending and receiving machine. So any frame less than 64 bytes in length is considered a collision frame or a runt frame and is automatically discarded. Frames with more than 1500 bytes of data are considered to be jumbo or baby giant frames. And so basically, when you subtract all the header information, it means the data section can be 1500 as a maximum. The size of transmitted frame is less than the minimum or greater than the maximum. The receiving device drops that frame. Drop frames are likely to be the result of collisions or unwanted signals. They are considered invalid. Jumbo frames are usually supported by most fast Ethernet and gigabit Ethernet switches and NICs. Okay, so the MAC address. So an Ethernet MAC address consists of 48-bit binary value expressed using 12 hexadecimal characters. So given that 8 bits is 1 byte and a common binary grouping, and so basically you've got, of course, 8 zeros through to 8 ones are the possible values, and so for each byte, 00 through to FF are the possible values. So of course that is equivalent to that, and this is equivalent to that. When using hexadecimal, the leading zeros are always displayed to complete the 8-bit representation. So for example, the binary value quad 0 1010 would be 0A. Hexadecimal numbers are often represented by the value preceded by a 0x, and that's just to distinguish between decimal hexadecimal values, because 73 just by itself, it could either be hexadecimal or digital, couldn't it? Because there's only the numeric values in there. And so if you put a 0x in front of it, people will know, oh, this is hexadecimal. And so 73 in hexadecimal is much bigger than 73 in decimal. Hexadecimal may also represent a subscript 16 or the hexadecimal number following by a H as well. So you can actually do it that way as well. But I've got to admit, I've only ever seen 0x myself. In an Ethernet LAN, every network device is connected to the same shared media. MAC addressing provides a method for device identification at the data link layer of the OSI model. An Ethernet MAC address is a 48-bit address expressed using 12 hexadecimal digits. Because a byte equals 8 bits, they also say a MAC address is 6 bytes long. All MAC addresses must be unique to the Ethernet device or Ethernet interface. To ensure this, all vendors that sell Ethernet devices must register with the IEEE to obtain a unique 6 hexadecimal or 24-bit code called the Organization Unique Identifier, or OUI. An Ethernet MAC address consists of 6 hexadecimal vendor OUI followed by a 6 hexadecimal vendor assigned value. So basically, the first half of a MAC address identifies who made the device. The second half is just a unique number. And so if you wanted to make Ethernet devices, by all means you can, but you need to register with the IEEE to get a unique or organizational unique identifier. And then from there, with 24 bits, that's 16 million devices you can create. So that should do you for a while. Now, if you've ever looked at Ethereal, Wireshark, sorry, I was using the old name for a second. Sometimes when it shows MAC addresses, it will actually show a name followed by the last 24 bits. So basically, Wireshark knows who has registered each code, and so it will then, of course, it actually has a database that it can look up and actually show you who made it. So sometimes it might say HP, or it might say Cisco, or it might say, actually I was looking at it yesterday, and a Ricoh printer, it knew that Ricoh, the Ricoh code. So that's how Wireshark can use that OUI. All right, frame processing. When a device is forwarded a message to an Ethernet network, the Ethernet header, including the source MAC address and destination MAC address. When a NIC receives the Ethernet frame, it examines the destination MAC address to see if it matches its own MAC address. And so if there is no match, the device discards the frame. If there is a match, it passes the frame up the OSI layers where the decapsulation process takes place. And so that's why I was saying that with the router. And that's why the destination MAC address is the router. So it will look at it and actually deal with it instead of just tossing it. So Ethernet NICs will always accept frames if the destination MAC address is a broadcast or a multicast group of which the host is a member. So any device that is a source or destination of an Ethernet frame will have an Ethernet NIC and therefore a MAC address. This includes workstations, servers, printers, mobile devices, and routers. Okay, so Unicast MAC address is just the MAC address that's been hard-coded into the NIC. And so they are used for layer 2 unicast, broadcast, and multicast communications. But the Unicast Mac address is the unique address that is used when a frame is sent from a single transmitting device to a single destination device. The process that a source host uses to determine the destination MAC address associated with the destination IPv4 address is ARP, or Address Resolution Protocol. The process that a source host uses to determine the MAC address with an associated IPv6 address is called neighbor discovery. So ARP doesn't exist in IPv6. They've replaced it with a process called neighbor discovery. So the source MAC address must always be a unicast. Now, you can also have an Ethernet broadcast address or frame. And so the Ethernet broadcast frame is received and processed by every device on an Ethernet LAN. The features of a broadcast are as follows. The destination MAC address will be all Fs. So of course an F is 4 ones, and so in binary it's 48 ones. It is flooded to out all Ethernet switch ports except the incoming port, and it is forwarded by is not forwarded by a router. So Ethernet switch ports will always forward broadcasts. Routers normally do not. If the encapsulated data in the IPv4 broadcast packet, this means that the packet contains a destination IPv4 address that has all ones. So 255, 255, 255, 255 is the broadcast address for IP. This numbering in the address means that all hosts on that local broadcast domain will receive and process the packet. Now, multicasts. Has anyone heard of multicasting before? Okay, it's basically a unicast is one source, one destination. A broadcast is one source, everyone's a destination. While with multicast, there's one source and there's a group of hosts that are interested in that. And so that's a multicast. Basically, when do we use multicasts? Well, IPv6 uses them a fair bit, but other uses for multicasts can be things like, have you ever seen them building up a classroom full of computers? So basically they multicast just to that group of computers that are interested. And so, no one sits down and with a CD or DVD and installs Windows on these computers. That's a slow process. Also, I don't think these have got DVD drives. Mind a little technicality. And so what they do is they boot from probably there's may well be some boot information in the DHCP server. They can actually boot to a server, and they can then transfer an image of a workstation that works on this in this classroom to all the PCs in the classroom. And so they can actually do all, I'm assuming, 21 PCs at the same time. And so that makes things a lot more efficient. And so you can do a room full of computers in about an hour. If you had to do all 21 computers individually, that would take you more than a day probably. And so it's more efficient. And so then they need to, of course, have a way that each computer is identified individually, because they'll need to have different names and other such stuff. And so that's another use that's actually used for multicasting. But anyway, back to this. So there is a destination MAC address of 01005E when encapsulated data is an IPv6 packet, and a destination MAC address of 3333 when encapsulated using IPv6 packets. There are other reserved multicast destination MAC addresses for when encapsulated data is not IP, such as spanning tree. It is flooded out all Ethernet switch ports except the incoming port, unless the switch is configured for multicast snooping, and then it will only go to the ports that are interested. Now, it is not forwarded by a router unless that router is configured to route multicast packets. So there are actually separate routing protocols for multicast. Because multicast addresses represent a group of addresses, sometimes called a host group, they can only be used as a destination of a packet. The source will always be a unicast address. As with unicast and broadcast, a multicast IP address requires a corresponding multicast MAC address. So there's actually a part of the IP addressing range that's set aside for multicast. There's also a part of the MAC address range that's set aside for multicasts. Okay, so the MAC address table. So a layer 2 Ethernet switch uses layer 2 MAC addresses to make forwarding decisions. It is completely unaware of the data protocol being carried in the data portion of the frame, such as an IPv4 packet, an ARP packet, or whatever it might be. The switch makes its forwarding decision based solely on the layer 2 Ethernet MAC addresses. An Ethernet switch examines the MAC address table to make a forwarding decision for each frame. Unlike legacy Ethernet hubs that repeat bits out all ports except the incoming port. When a switch is turned on, the MAC address table is empty. So the MAC address table is sometimes referred to as content addressable memory or a CAM table. That's just the way that they sort of store the MAC addresses so you can efficiently find them. Now, how do switches learn MAC addresses? So every frame that enters a switch is checked for new information to learn. It does this by examining the source MAC address of the frame and the port where the frame entered the switch. If the source MAC address does not exist in its table, it is added to the table along with what port it arrived on. If the source MAC address does exist, the switch updates the refresh timer for that entry. By default, most Ethernet switches keep an entry for 5 minutes, but of course, if your host sends a packet at least once every 5 minutes, that timer will be refreshed and it won't expire. Now, if the source MAC address does exist in the table but on a different port, the switch treats this as a new entry. The entry is replaced using the same MAC address but with the more current port number. So it's assuming that someone's just plugged it into a different port in the switch. Now, how do we find the destination MAC address? So in other words, when we're forwarding. If the destination MAC address is a unicast address, the switch will look for a match in its table. If the destination MAC address is in the table, it will forward the frame out the specified port. If the destination MAC address is not in the table, the switch will forward the frame out all ports except for the one it arrived on. This is called an unknown unicast. So basically, when it knows the destination, it will actually forward the frame to the host. If it doesn't know the destination, it will do what's called flooding. It will send it out all other ports. If the destination MAC address is a broadcast or a multicast, the frame is always flooded out all ports except the incoming ports. Filtering frames. So as a switch receives frames from different devices, it is able to populate its MAC address table by examining source addresses of every frame. When a MAC address table, the switch contains the destination MAC address, is able to filter the frame and forward out a single port. Okay, switch speeds and forwarding methods. Now, we're talking about forwarding methods first. So there's two possible methods, well, two major methods, store and forward and cut through. Now, store and forward is actually the switch starts saving the frame as soon as it starts arriving, and it waits for the entire frame to arrive, and then it will do the error detecting, and then it will either then forward the frame if there's no errors, or will drop the frame if there are errors. The faster way to do it is called cut-through switching. And so basically, only enough of the frame has to arrive that the entire destination address arrives. Then the switch will look up, do its lookup in the table, and then start forwarding the frame as soon as it knows what port it needs to send it down. And so, so that's a much faster method, and so you get less latency with that method. Now, when I was buying, I bought some switches at home. I bought gigabit switches a few years ago, and I was looking at the methods, and all the little cheapy gigabit switches you buy at home, they are all store and forward. They do not do cut through. So you actually need to get a business, well, unless someone's brought one out in the last few years since I did my research. So you actually need a business class switch to do the cut through switching. A big advantage of store and forward is that it determines if a frame has errors before propagating the frame. When an error is detected in a frame, the switch discards the frame. Discarding those frames reduces errors and the amount of bandwidth consumed by corrupt data. So that's nice, but of course, how many errors happen these days? It's a lot more reliable than it used to be. While store and forward switching is required for quality of service analysis on converged networks, where frame classification with traffic prioritization is necessary. For example, voice over IP data streams need to have a priority over web browsing traffic. Now, cut-through switching. The switch acts upon the data as soon as it's received, even if the transmission is not complete. The switch buffers just enough of the frame to read the destination MAC address so it can determine which port should forward out. The switch does not perform any error checking on the frame. And so it offers the lowest level of latency by immediately forwarding a packet after reading the destination address. Because fast forward switching starts forwarding before the entire packet is received, there are maybe times when packets are relayed with errors. The destination NIC discards the faulty packet on receipt. Fast forward switching is the typical cut-through method of switching. Now, there is a compromise between the two, and it's called fragment-free switching. And so basically, remember a few slides, well, I don't know, it was earlier, Ethernet has a minimum frame size of 64 bytes. And so basically it waits for the first 64 bytes to arrive. If there's been no collisions, no errors, it will then start forwarding the frame. And so less chance of having errors, but not completely no chance, but it's just sort of a compromise between the two. So because most network errors and collisions occur in the first 64 bytes, this ensures that a collision has not occurred before forwarding the frame. And so it negates the possibility of forwarding a collision frame. But, of course, collisions only happen if you've got hubs or bus networks in your network. So anyway, now switches do need to buffer frames when they arrive. There's two ways you can do that. One is by port-based memory, so you basically have a queue for each port, and so you put it into a buffer, and then that port will just go through that buffer until it's empty. Then there's shared memory, where all frames just go into a common buffer, and then the frames in the buffer are dynamically linked to the destination port, enabling a packet to be received on one port and transmitted on another port without moving it to a different queue. Shared memory buffering also results in larger frames that can be transmitted with fewer drop frames. This is important with asymmetric switching, which allows for different data rates on different ports. Therefore, more bandwidth can be dedicated to certain ports. Now, that is something we probably need to talk about. If you look at the switches in this rack here, they've often got two ports that are gigabit and the rest are fast Ethernet. And so basically, if I've got a workstation that's uploading something, sending something on the network, if it's arriving at fast Ethernet, it can't go straight to a gigabit port and be transmitted because it's not arriving quickly enough, because the gigabit Ethernet will take 1/10 of the time to transmit the data that a fast Ethernet would. And so it always has to buffer it then. And so it would actually have to wait for the entire frame to arrive before it then sends it on the gigabit link. Of course, if a host is downloading data, it will be arriving on the the gigabit link. And of course, it'll be arriving faster than it can be transmitted on the fast Ethernet link. And so you can start transmitting straight away on that fast Ethernet, but of course it's going to take 10 times longer to transmit it than it is to receive it. And so again, it's going to have to buffer it. So there is always going to be buffering on switches, especially if you've got multiple speeds on those switches. Okay, duplex and speed settings. So we've already spoken about full duplex and half duplex. Now you can actually manually set switch ports to be full or half duplex, or you can actually have them auto-negotiate, which is the default setting. And so, of course, basically the auto-negotiation, what a switch does with either other switches or hosts, is they try and look for the fastest, most desirable setting first. And so, if it's a gigabit port, hey, do you support gigabit full duplex? If they do, great, we'll use that because that's the best solution. But if one supports gigabit and the other one only supports fast Ethernet, well, you don't support gigabit. Well, let's try fast Ethernet. Do you support fast Ethernet full duplex? Oh, you do? Cool, let's do that instead. So that's the second best solution. And so Gigabit Ethernet ports only operate in full duplex, of course, but anyway. Now, duplex mismatches can occur. I got to admit, you don't see them often these days, thankfully. There was an older model of Cisco router that always had trouble negotiating with switches. It was 2600, so yeah, it's 20-year-old switch now, router now. But anyway, and I always had trouble with them, and so I used to have to go in, and you'd actually set, I want speed 100 because that was all it supported back then, duplex, full duplex, and so I'll do that on both the switch and the router on that port that it was using, and it would work beautifully. Just the order negotiation was just a little bit and so it can occur, and so setting it statically is an option. But if order negotiation works, just let it work. Now, auto MDIX. So remember we were talking about straight through cables and crossover cables a couple of chapters ago. And so that's auto MDIX. And so basically, as I said, newer hosts and switches support this automatic feature. And so, of course, the command would be MDIX auto to turn that on. You can actually turn it off as well. And so, yeah, but again, I've done it, but only to play with it. I've never actually had to do it. All right, so that's the end of the chapter. Hallelujah, they all say. So we've looked at how Ethernet operates in the data link layer and the physical layer. We've looked at Ethernet standards, define both layer 2 protocols and layer 1 technologies. Of course, we've looked at the sub-layers in the data link layer for logical link control and media access control. Ethernet frame fields are preamble, starter frame delimiter, destination MAC address, source MAC address, ether type, and then there's the data field, which of course is the IP packet, and then there's a frame check sequence on the end. Remember in the previous chapter it said start and stop flags? Well, actually, with Ethernet, there's actually a field in the control that actually has frame length, and so there's no stop field. And so there's the preamble, which is the start frame, but there's no stop field in Ethernet because in the header there's a frame size. MAC addressing provides a method for device identification at the data link layer of the ISI model. An Ethernet MAC address is 48-bit address expressed using 12 hexadecimal digits or 6 bytes. When a device is forwarding a message to an Ethernet network, the Ethernet header includes source and destination MAC addresses. In Ethernet, different MAC addresses are used for layer 2, unicast, broadcast, and multicast communications. A layer 2 Ethernet switch makes forwarding decisions based solely on layer 2 Ethernet MAC addresses, does not care about IP addresses at all. The switch dynamically builds the MAC address table by examining the source MAC addresses of the frames received on certain ports, or all ports. The switch forwards frames by searching for a match between the destination MAC address in the frame and an entry in its MAC address table. And so they use forwarding methods of either store and forward or cut through. So cut through has less latency, while store and forwards less error frames. And a compromise between the two is fragment free. Two methods of memory buffering is port-based memory or shared memory. There are two types of duplex settings used in Ethernet, so it's either full or half duplex. There's the end of the slideshow. Okay.